Hello, and welcome to Passive Fire Protection Systems in Industrial Applications, brought to you by Owens Corning. My name is Doug Fast, Technical Lead for Owens Corning. Also presenting is Alec Cusick, Technical Lead for Owens Corning. Today we'll be talking about the following topics, starting with an introduction to Owens Corning. Then we'll move on to fire safety and passive fire protection. We'll discuss standards and material selection. Then we'll turn the discussion over to Alec Cusick, who'll talk about fire-tested insulation systems and technical resources available for your passive fire protection project. Owens Corning is a global industrial and building materials leader with 3 integrated businesses dedicated to the manufacture and advancement of insulation, roofing, and fiberglass composite materials. Owens Corning offers a wide portfolio of insulation products that can be utilized in many different areas within modern industrial facilities. These systems can be designed to serve a multitude of purposes, including passive fire protection, energy efficiency, and sound isolation, just to name a few. Our product portfolio includes both open and closed cell insulation solutions, including FOAMGLAS Cellular Glass, fiberglass, Parac and thermofiber mineral wool, and FOAMGLAS extruded polystyrene. Let's move on to today's topics of fire safety and passive fire protection. The reason we want to have a fire protection system in our industrial facility is threefold. First of all, we want to protect against the rapid temperature rise of protected substrates, things like piping, equipment, pressure vessels, and structural elements that are supporting those things. Now, if we maintain structural integrity, that also means that those support systems aren't going to collapse and possibly rupture what's being supported. Finally, it also allows for the safe and controlled shutdown of equipment and allow time for firefighting personnel to arrive. Now, it might sound strange to talk about insulation and passive fire protection in the same sentence. But since insulation reduces the rate that heat can transfer into process equipment or structural elements, it becomes more apparent that insulation can serve as passive fire protection. There's a common misconception that insulation blocks the amount of heat that can pass through a given material. Insulation actually just slows the rate that heat energy passes through a given material. In the case of passive fire protection, the goal is to reduce the rate that heat enters the piping equipment and structural elements. When this is done, process elements will take longer to vent, which is a good thing, and structural steel maintains its strength for a longer period of time, delaying catastrophic failures. This allows a better chance of shutting down the equipment in a safe manner and more time for firefighting personnel to arrive. Now, incidents, while they're uncommon, can still be catastrophic. Some recent examples are Piper Alpha and the Deepwater Horizon disaster. Piper Alpha project was an oil platform located in the North Sea that exploded and sank in July of 1988. Killing 165 men. The other example, Deepwater Horizon, was an oil spill on the Gulf Coast of Mexico, which dumped a tremendous amount of oil in the Gulf of Mexico in April 20th of 2010. It's considered to be the largest marine oil spill in history in the petroleum industry. Here are a few examples of facilities that are best served with passive fire protection. Essentially, any facility that stores and handles flammable materials and potential combustion sources. Large amounts of fuel coupled with complex equipment highlight the need for passive fire protection. As you can see in the images shown, a fire at any one of the pipes affects the equipment surrounding, potentially causing a cascade effect in the event of an accident. When we look at the potential access we have to fire in some of these facilities, the need for additional time becomes apparent, whether it's an LNG facility, petrochemical facility, an offshore drilling platform, or an oil or a petrochemical refinery. Within different facilities exist various types of equipment to be insulated, many of which require passive fire protection. 2 applications for passive fire protection are process elements such as piping, tanks, spheres, and vessels, and structural steel. With process applications, what we're trying to do is increase the time for contents of the pipes, tanks, spheres, and vessels containing flammable materials to reach critical temperature, potentially causing venting, rupturing of the vessel or pipe, or an explosion. Passive fire protection allows for safe, controlled shutdown of process equipment. With structural applications, more time is provided until structural steel reaches 1,000 degrees Fahrenheit, where it loses a considerable amount of its strength, approximately 50%. The longer that we can maintain structural integrity, the longer the time that the structural element can support the pipe, tank, or sphere or vessel that's supporting a flammable liquid. If we were to leave these assets uninsulated, the temperature would rise more rapidly. Rapid temperature rises in process equipment can result in explosions. High temperatures in structural steel elements reduce the strength of the supports of elements containing flammable liquids, which could lead to the collapse of a supporting structure, potentially causing a spill. Imagine if the leg of the sphere shown in the bottom image were to be compromised. The contents could add to the fire if that sphere were to rupture in that. Sources of fire come from a combination of a flammable material and a source of ignition. LNG, petrochemical, offshore, and oil and gas refineries provide a fuel source for the potential fire. Sources of ignition that can potentially ignite flammable gases or liquids in these environments include the following: welding, electrical malfunction, static electricity, lightning, test equipment, auto ignition, loss of control of equipment, and absorbent insulations. Should the unthinkable happen when a flammable material meets an ignition source, plans must be made to minimize damage to the asset and, more importantly, safety. Now let's cover some standards that are frequently applied to industrial passive fire protection systems. One standard commonly referenced when designing passive fire protection systems is UL 1709, the standard for rapid rise fire test of protection materials for structural steel. This test evaluates the ability of protective materials, such as an insulation system, to withstand high temperatures and protect equipment and process lines in the event of a fire. It was originally designed for use on structural steel, but has also been adapted to cover protection for process piping, equipment, spheres, tanks, and vessels. The test involves attaching groups of thermocouples to a steel substrate and then covering it with a protective insulation system. The system is then placed in a furnace and brought to 2,000 degrees Fahrenheit over a 5-minute heat-up period to duplicate a hydrocarbon fire, which might take place in the facilities we talked about earlier. This test has a much faster heat-up rate than the fire testing used for buildings such as ASTM E119. The test continues until a group of thermocouples underneath the insulation is allowed to reach an average temperature of 1,000 degrees Fahrenheit, or a single thermocouple reaches 1,200 degrees Fahrenheit, at which point the test is concluded and the time rating is recorded. It should also be noted that UL 1709 also covers an extensive list of additional material properties. However, the rapid rise portion is commonly carried out independently for passive fire protection performance and is an acceptable methodology to determine system performance. Here we have a visual representation of 3 hypothetical pipes, all covered with different insulation systems being tested in this manner. As you can see, in 5 minutes, the furnace reaches 2,000 degrees Fahrenheit. The thermocouple groups underneath the insulation are then monitored. Whenever a thermocouple group reaches a temperature of 1,000 degrees Fahrenheit, or if a single thermocouple reaches 1,200 degrees Fahrenheit, the system fails and the time rating for that system is logged. In our example shown below, the time rating for substrate number 1 would be approximately 30 minutes. The time for substrate number 2 would be approximately 45 minutes, and the time for substrate 3 would be approximately 60 minutes. Another test method commonly used in the industry is ISO 22899, the determination of the resistance to jet fires of passive fire protection materials. This test method measures the resistance and protection provided by protective materials to the high velocities and temperatures associated with jet fire scenarios. It is used on structural steel as well as process piping, equipment, tanks, and spheres. It is frequently used in hydrocarbon process facilities to help protect these systems in the event of a breach of a high pressure line, which can result in a high velocity flame. In this test, a steel substrate is once again attached with thermocouples and then covered with a protective insulation system to be tested. The system is then exposed to a high velocity flame and allowed to heat up until a single thermocouple reaches 400 degrees Celsius, or 752 degrees Fahrenheit, above ambient conditions at the start of the test, which at the point of the time the test is started, that amount is recorded. Once again, we can see 3 hypothetical systems being tested in this manner. Immediately upon starting the test, the system is exposed to high-velocity jet fire, and the thermocouples are monitored. The systems are allowed to heat up until one thermocouple reaches 400 degrees Celsius above ambient conditions, at which point the test is concluded and the time rating is recorded. For example, substrate number 1 has a time rating of approximately 30 minutes, substrate number 2 has a time rating of approximately 45 minutes, and substrate number 3 has a time rating of approximately 60 minutes. Another consideration to be made when designing passive fire protection systems is the impact the systems may have on the sizing of relief valves. In hydrocarbon facilities, materials must frequently be kept at low temperatures in order to keep them stored safely in their liquid form. In many cases, depressurizing systems must be incorporated into storage tank designs to allow for the safe relief of pressure buildup due to vaporization in the event of fire or other failure. Passive fire protection offered by insulation systems may be considered when determining the size of these relief valves. There are multiple standards that provide recommendations for the design and structure of these pressure relief systems, including API 2000 and NFPA 30A. These standards contain equations for thermal credit taken for insulation systems, which restrict the flow of heat into the vessel in the event of a fire. Once again, passive fire protection systems may be considered in determining the relief valve sizing requirements for storage tanks of these critical low temperature processes. Now that we've covered common test methods, let's turn our attention to material selection for these applications. There are several ways that passive fire protection is used. First, we have insulation systems that at a minimum include insulation and jacketing. Next, we have intumescent coatings, which char and expand to form a type of insulative layer to reduce the rate of heat transfer, which slows the rate that the substrate heats up. Finally, we have hybrid systems that use a combination of insulation and intumescent coatings. It must be noted that in many, if not all cases, the insulation system will be sacrificed in the event of a fire. Insulations can melt, crumble, or be stressed beyond their intended use. At a minimum, the system would require complete inspection before returning to use with a new passive fire protection system. Key design consideration involves the flammable properties of materials to be used during construction. Usage of non-combustible materials in the event of a fire is preferred when designing safe commercial spaces. When we consider materials for use as passive fire protection, the first thing to look at is how the material performs when tested to some common fire tests used in the industrial space. First of all, we have combustibility, which is commonly referred to in industrial insulation datasheets and is the tendency of the material to burn or contribute to the fire as fuel. Ideally, an insulation does not lose its mass or increase the temperature of the fire or exotherm as it heats up. Test methods such as ASTM E136 and ISO 1182 are commonly used test methods used to measure combustibility. Flame spread helps to determine how far and how quickly a flame will propagate across the surface of a material when ignited. Ideally, we'd want something where a flame doesn't spread or spreads very slowly. ASTM E84 or CAN ULC S102 is used to measure flame spread. Generally speaking, most industrial insulations have low flame spread values. Finally, we have smoke development. It's the measure of how opaque or dense the smoke is that is generated by materials that's being evaluated for flame spread. The higher the smoke density, the lower the visibility, and the greater the danger of smoke inhalation to firefighters. Ideally, we want a material with low smoke development. Measurement of smoke development is done in conjunction with ASTM E84 or CAN ULC S102. Some additional key properties that we want to consider when we're designing passive fire protection are shown below. One of those would be thermal conductivity, which is a material property which measures the rate at which heat passes through a given material. The lower the thermal conductivity, the longer it takes for heat to pass through the material. Ideally, we want a material with low thermal conductivity. This is commonly referenced as the K value on product data sheets. Another property to consider is specific heat or specific heat capacity, and this is the amount of energy required to raise the temperature of a unit mass of a given substance by a given amount. For example, the specific heat of water is 1 BTU per pound Fahrenheit degree, whereas steel is 490 BTUs per pound per Fahrenheit degree. Generally speaking, the heavier the material, the more energy it takes to heat it to a given temperature. If you've ever tried to cook with a cast iron skillet versus an aluminum pan, you'll notice that it takes the cast iron skillet much longer to heat up. Finally, we have service temperature, and this is the maximum temperature that a material can safely and effectively function. Service temperature is defined by the manufacturer and may differ by end-use application. Exceeding the maximum service temperature can permanently change the material properties by degradation such as shrinking, melting, or warping. Now that we've talked about testing standards and methods along with desirable material properties, I'll turn it over to Alec, who will tell us about Owens Corning's passive fire protection systems.
Thank you very much, Doug, for that insightful background into passive fire protection. As mentioned, I'll now transition into one Owens Corning insulation material that may be suitable for your passive fire protection applications, and that is FOAMGLAS Cellular Glass Insulation. So for anyone that might not be familiar, just what is FOAMGLAS Cellular Glass Insulation? FOAMGLAS insulation is a lightweight, rigid material composed of millions of completely sealed glass cells. It's 100% closed cell, and it is inorganic in nature, which lends to some unique properties compared to other insulation materials in the industry. It also boasts a wide service temperature range as a thermal insulator from -450 all the way to positive 900 degrees Fahrenheit. Now, Doug discussed on a previous slide the significance of service temperatures for an insulation material, and this is a good indicator of the temperatures an insulation can withstand under typical normal operation. However, some insulation materials are able to exceed this temperature range temporarily in fire event scenarios and continue to provide passive fire protection as a sort of sacrificial material to aid in the safe shutdown of equipment and evacuation of personnel. And in this instance, FOAMGLAS will remain in place on a pipe, on a substrate, to provide the purpose of passive fire protection, even if this service temperature is exceeded. FOAMGLAS as an insulation material is completely impermeable, with a water vapor permeability rating of 0. It does not require the use of an external vapor barrier to achieve this, as the insulation itself acts as its own vapor barrier. It also boasts a relatively high compressive strength when compared to other insulation materials, making it suitable for direct buried and pipe support applications. It's also dimensionally stable, having a thermal expansion coefficient similar to that of carbon steel, making it suitable for wide temperature cycling applications. And of course, being 100% inorganic and made of glass, FOAMGLAS as a material is non-combustible and does not give off dangerous gases in the event of a fire, making it suitable for passive fire protection and fire stop applications. It's also resistant to the nesting activities of common vermin and is chemically resistant in a similar fashion to typical glass beakers that you might expect to find in a laboratory. Finally, it's easy to cut and can be prefabricated to many different shapes and configurations prior to arrival on a job site. Owens Corning also offers a full portfolio of FOAMGLAS accessories to be incorporated into these insulation systems. To name just a few, these include pit seal sealants to ensure a proper seal against vapor intrusion at terminations and joints between insulation sections, PC adhesives for securement on certain substrates, and pit wrap jacketings to provide freeze-thaw protection on the surface cells of the insulation. These accessories can be used in different combinations to achieve different insulation systems for a variety of applications. With that, we will now get into some of the specific insulation systems that Owens Corning has tested for passive fire protection applications. Before we continue, I want to outline the information you're about to see on the coming slides. Within the table, you'll see which test method was used for the system in question, the time rating that can be expected for that system, and common areas to specify the system, including process temperature ranges, types of equipment, and examples of relevant industrial facilities that it could be found within. Additionally, on the bottom, you can see an outline of the system makeup, including the insulation material and accessories used. One thing that I'd like to mention is that the time rating shown for each system may vary with substrate size, geometry, insulation thickness, and process temperature. Here's an example of a single layer FOAMGLAS system that's been tested to the UL 1709 test method. This is a system that consists of our FOAMGLAS 1 insulation with our pit seal 444NS sealant, pit wrap B100 jacketing, and 0.16-inch stainless steel cladding. This system could be commonly found on below ambient systems that might be present within a facility. And even though it's single layer, so it has a relatively low insulation thickness overall, this system was still tested for up to 30 minutes of time rating to UL 1709. We also have test data on some hybrid systems that incorporate multiple different insulation materials in the overall insulation system. Here's an example of a single layer of FOAMGLAS 1 insulation. Same thing with our pit seal sealant and pit wrap jacketing. but also with a single layer of ceramic fiber insulation on the outside of it, again with Owens stainless steel cladding. This could be found on below ambient systems, on piping equipment, tanks, vessels, commonly in oil and gas processing facilities. And this specific system has been tested for up to 120 minutes to the UL 1709 test method. Here's an example of a double layer foam glass insulation system, this time including one of our PC adhesives. This adhesive allows for the installation of this system on difficult substrates. One common example could be spheres that could be located within a facility. Oftentimes these systems could be below ambient, and in this double layer configuration, this system in particular has been tested for up to 120 minutes to UL 1709. And in addition to performing fire testing on piping substrates, we've also tested our systems on I-beam structural steel configurations. This is very easy to accomplish, again, by using foam glass with one of our PC adhesives to allow for easy securement to those difficult steel substrates that might make up an I-beam. In this instance, again, we use one of our PC adhesives along with our foam glass 1 with Owens 6-inch stainless steel cladding, and this configuration has been tested for up to 180 minutes of exposure. In addition to UL 1709, we've also tested many of these systems for ISO 22899 exposure to jet fire scenarios. Here you can see a similar below ambient single layer foam glass system that we showed a few slides ago, consisting of our foam glass 1, our pit seal sealant, and pit wrap jacketing, this time with a 027-inch stainless steel cladding over the top. And this system, when tested to ISO 22899, was tested for up to 30 minutes of time rating to a jet fire scenario. Here we can see the same hybrid system that features a single layer of foam glass insulation with a single layer of ceramic fiber insulation on top. Again, this was tested to ISO 22899 for jet fire scenarios and was tested for a time exposure rating of up to 90 minutes. And as one final example, here's a system that is composed of a single layer of foam glass insulation paired with an intumescent coating applied to the outside layer. This is an example of a hybrid system that leans on both insulation and intumescent materials to make a combined passive fire protection system. When this specific configuration was tested to ISO 22899, it demonstrated up to 240 minutes of fire exposure to jet fire scenarios. And this is just one example of the multiple ways you can configure hybrid systems using different materials to create a passive fire protection system. And now I'd like to wrap things up by covering some of the technical services and resources that Owens Corning has available. For those interested in specific systems discussed here today, or any of our other capabilities on passive fire protection, we do have third-party test reports available from laboratories where these tests were conducted. These reports cover the test procedures, system configurations, and detailed results. And we also have Lloyd certificates available for those systems that were specifically tested for performance against jet fire scenarios. Here at Owens Corning, we offer fire modeling and thermal calculation services to help in the design and selection of passive fire protection systems. These reports can help specifiers determine the appropriate system configurations to achieve fire protection performance that's required. Additionally, we maintain and utilize a full suite of proprietary thermal calculation software to help aid in the design for those who specify our normal insulation systems. If you have questions as to what insulation thickness or jacketing material to use in order to achieve a certain service temperature, if you're curious about cost savings potential, or have general questions about process control, we'd be happy to assist with a thermal calculation report tailored for your specific system. We maintain over 125 different commercial and industrial insulation system guide specifications. These are documents that can be used as a guide for engineers, specifiers, contractors, and facility owners to aid in the design, installation, and maintenance activities around these insulation systems. They include products to be used, drawing details, and installation guidelines to help achieve the best performing system possible. And we are also very willing to help review client specifications when requested and provide advice to our clients on to how to best improve their specifications if they're trying to achieve a certain goal. Here is an example of one of our detail drawings that we offer specifically for our adhered foam glass system for passive fire protection. We generate drawings like these regularly to help bridge the gap between specification and field installation, and to increase the confidence level that proper application techniques are being utilized on site. We also provide on-site support around process improvement and energy savings. We have multiple certified thermographers on staff, myself included. We can arrive on site to perform infrared inspection surveys and conduct heat flow measurement and analysis to existing equipment. We can then issue a current insulation condition report, evaluate energy losses and savings potential, and provide general advice on insulation system improvements to consider. Finally, we are seen as the industry leader in education, training, and project startup support. We hold frequent training sessions that allow us to build relationships with our customers through shared experiences. These allow engineers and specifiers to become more familiar with our systems, and it allows contractors to better understand how to effectively install these systems in order to achieve the best performing system possible. Here you can see one of our global training centers located in Houston, Texas, where we frequently host training opportunities like this. Please reach out to us with any interest on how we can collaborate with you and your team. With that, I'd like to take the time to thank everyone who was able to join us here today. My contact information, as well as Doug's, can be found in front of you, as well as the contact information for our FOAMGLAS technical services and training team. Please feel free to reach out to us with any questions or opportunities that we may have to collaborate with your team. At this point, I'd like to turn over the mic to Kelly as we open it up for any questions that may have come in throughout the presentation. Kelly?
Thank you, Doug and Alec, for a great presentation on passive fire protection. Hello, everyone. My name is Kelly Santiago, and I'm the marketing team for the Technical Installation Group here at Owens Corning. We had a lot of great questions come in during this webinar. Keep them coming. Let's go ahead and start to get them answered. First question, gentlemen. What is the hourly rating for foam glass?
I'll take this one. That's a great question. Foam glass doesn't have an hourly rating in and of itself because UL 1709 and ISO 22899 are system tests. You're always testing that as a system. So differences in geometry, substrate thicknesses, the kind of accessories that you're using, kind of jacket, all those type of things factor into that. And so it's a system test, not a test of a individual material. But so short answer is, it depends on the system, what that hourly rating is going to be. Okay.
Kind of related to that, a question, can hourly times be calculated for different configurations?
Okay, that's a good question. Foam glass has a vast amount of testing that's been done. And so with that information, we've been able to develop models that can predict hourly ratings in many different size applications and different types of substrates, insulation thicknesses, that kind of a thing. So if you do have an hourly rating that you're looking for in a specific configuration, please contact us, and chances are we have a model that we can apply to that to give a good estimate on what an hourly rating could be.
Okay. How can foam glass be used for passive fire protection with a maximum service temperature of only 900 degrees Fahrenheit?
Yes, that is a good question, Kelly. One we touched on briefly in the presentation, but some people do get confused about the difference between service temperatures and the qualities that you're looking for in a material for passive fire protection purposes. Essentially, in a fire scenario, in a lot of these facilities where you're putting passive fire protection systems on, your insulation can be your last defense on these types of substrates that you're trying to protect from dangerous temperature rises. While the surface temperature of an insulation shows the maximum temperature it should be used in typical operating scenarios of being on a pipe, for example, many insulation materials, including foam glass, are capable of temporarily withstanding temperatures higher than that service temperature. And for that reason, in passive fire protection scenarios, you can view these types of insulations as almost a sacrificial material that, while they may start to degrade from extreme heat from a fire scenario, in doing so, they are still providing thermal and passive fire protection from the substrate underneath. So while it's not recommended to use it for a typical insulation application at those temperatures, they do possess the material capabilities of protecting substrates as they exceed that surface temperature. So that's the reason that they can still be considered for passive fire protection above these temperatures.
Great, we have another question. What determines the type of the type of accessories that should make up a passive fire protection insulation system?
That is another good question. So you saw a wide variety of accessories used on some of the systems that we highlighted. Essentially, those are often determined by the type of application or the process temperature of what you're putting your insulation on. For example, if your process happens to be below ambient in temperature, vapor drive is going to be a concern of yours, and that's why you would be incorporating joint sealants, maybe a jacketing on the outside of the insulation system, things that aid in the integrity of the vapor barrier between insulation segments. And that will dictate, the type of system that will make up your passive fire protection system. In a similar vein, if you're installing foam glass, for example, on spheres or structural steel I-beams, our adhesives are very good at allowing those sorts of applications on weird substrates that it's hard to get metal banding to really be the only physical securement for. So that's the reason why we tested a wide array of configurations and why you might see or use different accessories on your passive fire protection systems.
Okay, great. Thank you. Well, that was a lot of great information in the webinar and a lot of great questions that came in. Thank you to both Alec and Doug for your time, and thank you, audience, for taking the time out of your day to join us for this webinar. Make sure you follow us on social media. Make sure you check your inbox for future webinars. Thanks.